why we need a new test. We were talking last week about hypothesis testing. We're testing a population proportion. Now we've got to talk about testing a population's mean or average. We're going to call that mu because we don't know what it is, but we know it's out there. It's mu. By using the sampling distribution on X bar, which is the guy we actually have. That is what we're going to chit-chat about today. That's what we're going to chit-chat about today. Fair enough? All right. So let's set up our four-step plan. We got 4 steps. I want to talk about hypotheses, define the variable we're interested in, crunch numbers, come to a conclusion. Okay, crunching numbers involves 2 steps. Getting the test statistic, getting the p-value. So let's start with step 1, which is setting up the hypotheses, the null and the alternative. I think, I'm going to try to make myself use the HA. I think your textbook uses H sub A, not H sub 1. Doesn't matter. It's the same thing. And different references flip-flop back and forth. So we'll call it H sub A. All right. What's the variable we're interested in testing right now? Rather than just variable, what are we interested in finding out? Jack, say it again. You said it, I believe.
Whether or not their IQs were lowered after head trauma.
Good. And I'm going to put one word in there. Their average IQ was lowered, if that's okay with you. Whether or not their average IQ was lowered. So the variable we're testing is average. It's mu. And that's going to be the average IQ after head trauma. We're going to see if it's significantly lowered. Statistically significantly lowered. It might only be 99 points on average, but that might be statistically significant. I don't know. Let's crunch the numbers ourselves first. Let's set the hypotheses up. Pick one of those hypotheses and tell me what it's going to be. Pick one. Using the symbol. I'll get you started. I'll put the U in there. Pick either one of them and tell me, complete it for me. Using what Jack just said. Jack, say it one more time.
The average IQ after head trauma.
Is lessened. Good. That's the claim, right? That's the claim. We've lessened the average IQ. All right? Let's do it. Who feels brave? Give me one of those 2 hypotheses. Now you have to know what number to use, but that number's given to you and then it'll lead up to the data. And hopefully you might remember this from 243 as well, as far as what that number should be. Who's feeling brave?
Mu is equal to 100.
I love it! Which one's that going to be, Will?
The null hypothesis.
Your null? Why would it be equal? Will says mu is equal to 100. Why would it be equal to 100? If you believe that head trauma lowers IQ, what do you go into your study believing?
You want to assume that it stays the same.
You want to assume it stays the same, Eric? Thank you. Assume it stays the same. Assume nothing changes. Good. Chip over here. Chip over here. Say that again. I like that a lot, Danielle. I like that a lot because that's the opposite of equals, isn't it? But Ryan, state your claim again. That's in the article. And I like what you're saying because this is why I don't like the convention that's been accepted. Let's come back to that, okay? State your claim again, Jack. That average IQ after head, or was it Will? You define the variable. When someone has head trauma, it is believed by the researchers that average IQ is what? Is lowered. So the claim that we want to test, and Danielle, I love what you said though, the claim we want to test is actually this. That's why, technically speaking, mathematically, this guy up here should be greater than or equal to. But convention says we just put equals. I have no problem with you putting this. And here's my suggestion to you guys as you're kind of learning the ropes of hypothesis testing. My suggestion to you is find the alternative hypothesis first. Find the alternative hypothesis and write that down first. Does that make sense? So if you can read the words and say, oh, the claim is that it's less than 100. Put that in. Then you know what the null has to be based on that. And it doesn't matter if you put equals or less than. pretty much every null hypothesis is going to be equals. And the opposite of equals, as Daniel correctly said, is does not equal, and sometimes we actually want a two-tailed does not equals test. Sometimes we do want that. In this particular one, though, it's a one-tailed test because we're trying to see if it's a lesson. Danielle, is that okay? And it's Laura, go ahead.
Oh, I missed why you put mu is greater than or equals to 100.
In parentheses.
Yeah.
Either one of these is acceptable, and here's why. All I'm saying is, this is convention, Laura. You're going to see equals pretty much everywhere nowadays. Back in the day, when I was learning this, these were polar opposites, as they should be. And when I draw the curve, and we actually test this, you'll see why. You'll see why. But the idea for me, mathematically, I like seeing them polar opposites like this, but the convention is that they accept just equals now. So that, it's not that one's right, one's wrong, they're both acceptable. This one's mathematically perfect, and this one's statistically okay. I like this one better. And Jackson, he's like not because it is the polar opposite of what you're testing. And it's also reflected in the null curve that you draw and test against much better than the other one. So, I'm sorry for the confusion, it's one of those conventions the statisticians have adopted that doesn't make a whole... The problem with it is, the conventions are accepted by people that have been doing this stuff all their lives, so mentally they're just like, oh, this is great, blah, 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 blah. But students that are learning it for the first time, it gets confusing. So that's why either one. If you've made peace with this one, use it. If you haven't, use this one. I'm down with either one. Is that fair? Mm-hmm. Okay, thank you. I saw another hand went up, maybe? I thought maybe, but I'm seeing things. It's okay. Now, I mentioned a null curve. The null curve is going to look the same. The null curve is going to look the same as it has in the past. You're going to have a beautiful curve like this. It's going to have an average. We're going to call it 0 because it's been normalized, it's been standardized to 0. We know that 0 really doesn't mean 0, it really means whatever value is in the null hypothesis, which in this case is 100. We know it doesn't actually mean 0. Ooh, hello. Fair enough? Decent, okay, good. We're trying to see if head trauma lowers IQ. Lowers. How many tails is this test going to have if it lowers IQ? How many tails? How many tails? Just one. Just one, because we're just trying to see if it lowers it. If it raises IQ, we'll be pleasantly surprised. We'll be selling 2x4s with special handles on them to go out and raise their IQs. But we're trying to see if it lowers it. We're trying to see if it lowers it. So in other words, let me ask you a question. If your test statistic lands here, are you going to claim that IQ is statistically significantly lowered? What's your gut feeling? Probably not. How about over here? No, definitely not. How about here? How about here? Okay, now we're starting to like, okay, maybe if we're over here, so somewhere, we're not going to identify it exactly yet, but somewhere out here, yes, somewhere out here is going to be a critical value, and over here is how much area. How much area is out there in that red that I just colored? But standard, what do we use? 5%. It's 5%, standard. And if our IQs, if our average IQs fall down past that value, then we start saying, okay, something's up. It looks like we were expecting IQs to still be at 100 or higher, but it looks like they're not. They're significantly below where they should be. Laura, to go back to your question, which is a very good one, the reason I like this is because I think this sign better indicates this part of the curve. The equals part would be this, and the greater than part would be this tail over here. It's still part of the 95% confidence interval on the null. It's just on that side of it. Is that fair? Not to over-answer your question, but it's a very, very good one. Rachel, go.
Okay, so I was writing down what you were saying, I missed the last part.
That's okay. That's why I'm glad I recorded.
So when you were drawing the arrow over it, it said if your
Yes.
average IQ ends up being lower, or at or lower 5%, what was the rest of that sentence?
Then you're going to say to yourself, wait a minute, I was expecting IQ to still be at 100, or maybe even higher, but definitely around 100, and it's way too low to make me think that it's still 100. I think there's some other lower curve. And I don't know where it's going to come out yet. All I got is data. I'm not sure where it's going to come out yet. We'll get to that. But that's all. If it gets so far down, into this red region, you start saying, I think I'm wrong. I think this is wrong. I think this is right. The smaller your p-value gets, the more you believe this. And you start believing this as soon as your p drops below 5%. Fair? That's the same as it will be the entire term. Right? The entire back half of this term, small p-values mean you believe this. Big p-values mean you believe this. I mean, that doesn't change. The only thing that changes is how we crunch our data. That's it. That's it. Cool? So what do you think? What do we believe? Let's process some data. Let's process. Get that data in your TI. Let's process. Let's shut this down for a moment.